Welcome to today's webinar. The subject of today's webinar is going to be mastering hybrid meshing for a horizontal axis wind turbine. The specific geometry that we're using today is called the CX100. It's a fairly standard horizontal axis wind turbine geometry, and we'll be putting a hybrid mesh on that. Presenting today will be Dr. Chris Sidoroff. He's a sales engineer at Pointwise. He's been here for coming up on 4 years now. Chris got his PhD at Syracuse University, working in the area of CFD analysis of a personal micro environment. Actually doing the driving today will be Travis Kerrigan. Travis is one of the newest employees at Pointwise. He's been here since May. He just finished up his master's degree in aerospace engineering at the University of Texas at Arlington, where he did optimization of a vertical axis wind turbine. And I'm Rick Matus. I'm the VP of Sales and Marketing here at Pointwise, and I'll be moderating today. For those of you who've attended our webinars in the past, we're doing things a little bit differently this time. We're actually going to answer questions during the webinar. So if you have anything that occurs to you while we're presenting that you want to have answered, you can type it in, and we'll answer those when we come to appropriate points during the webinar. And as we have in the past, we'll also have a question period at the end. So if you do want to save up your questions, you can save them up to type in at the end, or at the end, if you have a microphone, you can also ask questions verbally. So with the introduction out of the way, I'll go ahead and turn things over to Chris.
All right, thanks a lot, Rick. Thanks for the good introduction again. So we're going to be talking about mastering, basically techniques for doing hybrid meshing on horizontal axis wind turbine blade. Just to clarify a little bit more about the questions and what you're going to see today. So the first thing is, as opposed to some of our past webinars, we're actually going to show almost the entire meshing process right from beginning to end. We'll be showing about 95% of it, so you'll see essentially a CFD ready mesh at the end of the webinar. And then a little bit about the questioning. I'll do my best to answer questions throughout the webinar when there's some kind of some appropriate times. But if your questions are going to require maybe some sort of additional demonstration, possibly using the software, maybe I'll just try to leave those questions to the Q&A period. Or if it requires some really in-depth, some in-depth discussion, we can work with you one-on-one, after the webinar offline. So with that. Rick already kind of mentioned what the geometry is, so I'll probably just describe it to you in a little bit more detail. So this is just a couple of pictures of what the blade looks like. If you're not familiar with it, again, it's called the Sandia CX100. It's a 9-meter radius blade. Just a couple of kind of notable features on it. It doesn't have a flat back. The trailing edge is sharp, and also the tip is cut off kind of, and has that airfoil shape. It doesn't have a, kind of a more advanced tip that you might see in some more modern designs, but a lot more information available on the Sandia website for it, windpower.sandia.gov. So, at this point, I'm going to give a little bit of a background on why, a CFD engineer would be, concerned about meshing on a horizontal axis wind turbine blade. So, horizontal axis wind turbines, as we know, generate power through lift. And so efficient designs are going to need to have a low drag. The idea is to get, an efficient design, we want to maximize the lift over drag ratio. So we need to look at what factors are affecting the drag on the blade. And so the two predominant aerodynamic drag components in this type of analysis happen in the viscous region near walls in the boundary layer, and also in the wake, where we have some sort of deficit in the velocity. So, it makes sense that resolving the boundary layer and the wake, reliably and accurately are kind of the key to, a successful analysis. So, this begs the question, what do I need to do in terms of my mesh to help achieve this? So I'm going to back up a little bit and just talk about just meshing in general. We can think about meshing in general from kind of two ends of the spectrum. We have, the more traditional structured meshing approach, where it's 100% hex cells, body aligned, point match blocks, and so it's fairly well known. And over many years of work, it's they've been recognized as generally providing the highest fidelity solutions, but unfortunately they're relative to maybe a more modern meshing technique, they tend to be much more time intensive. But on the right, so we have the unstructured approach, kind of at the other end of the spectrum, requiring very little time on using with modern meshing techniques. In this case of the CX100, I mean, if we were just doing a fully unstructured mesh, it would literally take just a few minutes to make it. But the trade-off is, definitely some sacrifice in the fidelity of, the calculations that we're doing. So I kind of, you may have heard this, and I just mentioned before about structured meshes being, very high fidelity, and so there's you won't wonder, what is it about a structured mesh that makes it so desirable? So, I mean, I think I can break this down into maybe two kind of key concepts. One is just simply point efficiency. It's maybe the most obvious. So I just have a very simple problem here, just a back step, just showing you the differences. And so you can see in the case of the structured mesh, I have about half as many elements, so half as many cells as the equivalent, Delaunay unstructured mesh. And so in both these cases have the same number of points in the boundary. I just generated the interior with a different method. And this is further exacerbated in 3D, where that ratio, as opposed to being 2 to 1, is more along the lines of about 5 or 6 to 1. So you get considerably, higher cell count. Now the second, point that kind of that makes structured meshing so attractive is this notion of body-fitted structure meshes, grid alignment, aligning the grid with your flow, giving me a higher accuracy. So, that's just kind of a talky way of explaining. So, well, what is it about this aligning the mesh with the flow that gives us more accuracy? So, just a very simple, just comparison between, the quad cell, the structured mesh on the left versus the tri-cell or the unstructured mesh on the right. And this is I'm just simply showing you a flat plate flow. So we have no gradients in the streamline direction, and the gradient is strictly in the normal direction. And so what I'm looking at here is I'm showing you the Taylor series expansion about the cell center from the cell center to the face. And why is that? Well, I mean, if you look at cell-centered finite volume methods, where this is the numerical technique that we do to get the values to the face, because we have to do an integration around the faces of the cell to accumulate the values at the cell center. So this is a very important step. So in the case of the structured mesh, where I have a face the faces are aligned with the flow gradients, that the truncation error terms in that expansion essentially cancel out any of the truncation error terms, and so we have essentially a really high approximation from the cell center to the face. But not so in the case where with the triangle, where there's a remaining delta between the location of that cell center and the face center. So that's, and it may vary from solver to solver, but the general concept still applies no matter whether it's a self-centered or a node-centered or maybe some FEA-based algorithm. So again, another question that we can ponder is, when can I get away without using structured meshes? Well, I think the most obvious is time. I mean, it's kind of funny that, my boss told me I can only spend 1 day meshing, but there's a lot of truth to that. Is that generally time is money, and we can't spend forever working on our meshes. I mean, in a perfect world, yes, but that's not the case. So maybe getting back to a little bit more of the discussion about flow alignment. So when the flow path is unknown or changes rapidly in the case of maybe some sort of transient simulation, it would make sense that structured meshes definitely lose a benefit. If we don't know the flow path a priori, then it's pretty difficult for us to kind of align the grid lines with the flow. Another big benefit for unstructured meshes that we're pretty aware of is that they provide a lot more control or flexibility for localized clustering, and we can look at one particular area, pack in a bunch of cells, and that clustering does not affect far away. Whereas for a structured mesh, I may apply some sort of localized clustering, but just due to the nature of a structured mesh, that resolution control is going to possibly propagate into an area that we just simply don't need it. So, kind of getting back to the reason for this webinar today is hybrid meshes are just a good compromise between effort and accuracy. So so what we want to do is we want to put a hex, or in the case maybe a prism, or a prism mesh is where we take a triangulated surface and extrude layers. again, definitely better than purely tip mesh. So we want to put these prism or hex regions, zones in the important regions, so boundary layers and lakes. And in the case I'm going to show today, for compressible flows, we all know resolving shocks is important. And then for multi-phase calculations that are concerned with free surfaces, we want to resolve that sharp interface. So it's again fairly well known that trying to get a hex hex type cell in that region is important. And then we just put unstructured elsewhere just for the simplicity of meshing, kind of away from the flow gradients where it's maybe not affecting the accuracy of what we're interested in so much. So just one last figure that I'm going to discuss here before we get into the actual demo itself. This is a figure that I reproduced from a very excellent paper by Tim Baker called Mesh Generation Art or Science. This paper just is a nice discussion about meshing techniques and their effect on solution accuracy and a variety of different techniques. So again, this is just kind of a summary of what I was just talking about, where on the bottom right we have the unstructured technique in the orange box. Again, very easy to use, but fairly well known to be the least accurate of all the techniques. And then all the way on the top left, we have the multi-block structured, and by multi-block structured I mean we have many structured volume meshes, and they're connected one-to-one on their interfaces. And so again, this is well known to be one the most reliable and accurate meshing technique. And so Tim in his paper actually suggests that maybe the most optimal meshing technique should lie along the diagonal of this chart, and you can see that the blue box, which we're going to be talking about today, hybrid meshing, kind of falls in that region. So at this point, we're going to get away from this just introductory discussion and get into the actual demo itself. Just before I let Travis loose and we start working on, start assembling the pieces that are going to create this mesh, I just want to give a quick description. So this is the part that's already kind of pre-done. He's already done the surface mesh. You can see there's an unstructured mesh on the hub, and he's not showing the whole blade, but the same character of that structured mesh on the blade carries all the way from the root to the tip. And the only thing that's a little bit fancy in this case is that he has this kind of structured domain, structured surface mesh around the root of the blade itself, and he's going to use that to help facilitate creating this I'm going to call it a collar block or a collar volume mesh that's going to allow him to transition between the prism extrusion that we're going to do off the hub and the blade extrusion that we're going to do off the blade. So with that, I'll let him get going. So I'm just going to, again, I'm going to kind of narrate what Travis is doing. I'm not going to be able to explain every little step he's taking. Some of them are just fairly elementary things in Pointwise, but I'm going to try to just discuss some of the most important things he's doing. So what he's doing, like I mentioned, he's going to create this collared region at the root of the blade, and he's actually going to create a series of grid curves, which we call connectors, and surface meshes, which we call domains. And he's going to use those to create a framework by which he can assemble a structured volume mesh in this kind of collar region. And the reason why he's going to actually manually assemble it as opposed to possibly doing an extrusion, and it's just due to the character of the way the hub and the root of the blade kind of meet each other. So I'm just going to get, when he gets a chance, he's just going to rotate it around just so I can show you from the side how you can see on the downstream side of the hub how the distance between it and that surface mesh you created is much shorter as opposed to the upstream side. And so if we tried to create an extrusion with Pointwise to do that, the cells on that downstream side are going to pile up, and they may, it may result in kind of less than optimal cells. And so it's best that we manually create that mesh there, so we have full control of exactly what the cells are doing. So again, these are good opportunities for you to go ahead and ask questions. I'll do my best to answer them. All right. So Travis is just going to almost finishing up this piece here. So what he's going to do is he's going to take this. He just assembled the actual structured volume mesh. Now, just before he leaves this part and actually creates the prism extrusion on the hub, what he's going to do is he's going to split this structured volume mesh into a couple pieces, and he's going to do that um, strictly to create topology on the outer part of this structured volume mesh, and he's going to use the topology that's created from that. He's going to use that to guide the prism extrusion, so that when that prism extrusion comes up the side of this color mesh, that it becomes point matched. So I got one question from the audience here from Tony McDaniel. He's just asking what version of Pointwise you're using. I'm using the latest available version of Pointwise you can download from website. It's version 16.04, release 3. Okay, so Travis just finished up the topology splitting on that. So what he's going to do is now he can go ahead and proceed with that prism extrusion from the hub. And so this is where, so the first step in doing that is he needs to constrain that extrusion both on the sides of the hub as well as in that inner region where it's going to match up with that color volume mesh that he created in the first step. So because we're doing a periodic simulation, we're only simulating one of the blades, and there's 3 in here. We have this 120-degree sector region. He's ensuring that when this extrusion comes off, that the extrusion stays constrained to these periodic surfaces that exist in the geometry. And then the last one is to constrain the inner edges of this extrusion so that they match the structured topology that he created just before this when he did the block splitting. And so that when the extrusion is finished, that the edges of that extrusion are going to be point matched with that inner structured volume mesh. So I'm going to let Travis finish this up. I have another question from the audience. Derek Alexander, he's asking, how did you define the structured curve in the hub? So at the very beginning, before Travis had started, we'd showed that surface mesh, and he had that very nice looking structured kind of mesh that was a ring around the base of the blade. And all Travis would have done in that case is he would have taken the connectors, so our terminology for grid curves, he would have taken the connectors and done a 2D domain extrusion that would be database constrained to the hub. And then he would use boundary layer parameters that were what he's using today. And for those that are interested, the boundary layer parameters he's using today is a delta S of 0.001, a growth rate of 1.2, and he's actually has 12 layers in his boundary layer. Okay, so now we finished Travis has finished the prism extrusion on the hub itself, and now he's going to use a very similar process for doing the extrusion on the blade itself. Now, while he goes and does that, I'm just going to give a brief explanation as to the differences between doing an extrusion with a structured domain versus an unstructured domain. First, the most obvious is that you're going to end up with a hex volume mesh instead of a prism volume mesh. But by default, when you do an extrusion with a structured domain, creating this structured volume mesh, it's going to default to use the hyperbolic extrusion technique. And the benefit to using the hyperbolic extrusion technique is that it's equation based, and it has all this smoothing automatically built in, so that when it creates the volume mesh, it makes a very smooth and very orthogonal mesh. And Travis is going to show that here in a second when he gets finished. And so he's just going to select those just to highlight that. So you can see, just zoom in a little bit more for me, Travis. So we can see that this is the end of that extrusion at the blade tip, and we can see that the grid lines emanating and normally from the blade are very orthogonal with the blade, and then all the circumferential lines are very smooth, and so this creates this very high quality boundary layer resolved mesh. So to finish that up, at least the part around the blade, he's just going to do a translation extrusion from the tip, and so that we can have some better quality cells in the tip that can help us resolve the tip vortex. So I got another, I'm going to answer a few more questions from the audience here before we kind of move on to the next part. We got a question from Ozer Aydin. Excuse me if I mispronounced that. He's just asking, would the mesh be ready for Fluent when we're done? Absolutely. This is a mesh that's very amenable for doing analysis in Fluent. Got another question from Hin Fan Lao. He's asking about, can you control clustering in the unstructured mesh? Maybe expand this question a little bit. I'm missing some of it. Yeah, actually, Travis is going to go. He's going to move on to the part where we create the wake region behind the trailing edge of the blade, and he's going to actually show some of the techniques for doing, changing the resolution in unstructured mesh. So I'm going to let Travis go and start and beginning to create some grid framework for creating. What he's going to do is he's going to create a circular sector region in the wake or behind the trailing edge of the blade. That he's going to use to create some sort of wake resolution with using prism cells. Let's see, I have another question from Tony McDaniel. He asked about, was the tip mesh unstructured? Because he began with Travis began with at the tip there was two domains there. There was a structured domain and an unstructured domain, but he did a translational extrusion. So from the structured domains, the block resulting from that would be hex, and then from the triangular domain, the resulting extrusion from that would be prism. So it would technically be, again, another hybrid where we have a hex block as well as a prism block. I got another question from Swati Saxena. Did you use a database file for reading the geometry for the hub and the blade? I'm not sure if I'm going to answer this quite right, Swati, but there is a single geometry file. It's an IGES file that we use for this, and that contained not only the hub and the blade, but also the geometry for creating the far field. All right, so I'm going to catch up to Travis here a little bit. So now you can see he's created these 3 grid curves that are kind of defining this circular sector region. And just for simplicity, Travis has went ahead and just assembled an unstructured domain in this semicircular region, or this, excuse me, circular sector region. And the reason he did that, again, was just for simplicity. Again, it's a balance between time and effort. Somebody could ask, well, I would really prefer to have 100% hex cells in the wake, and that's absolutely fine. And if that were the case, and maybe an alternative approach might be to use maybe more of a kind of a rectangular looking topology instead of this kind of this circular sector region. But absolutely, it would just take maybe 5 or 10 minutes more, as opposed to just Travis is going to literally do this in about a minute or two. So before he actually does the prism extrusion to create this wake block, he's going to actually change the resolution of the points. And so all he did was just add a lot more points in that vertical connector in the wake region. So this may address that question that somebody had about how could you control the clustering in the unstructured mesh. And so he's done it by increasing the points along that connector. And in this step, he's actually changing the end spacings of the adjacent connectors so that we have a smoother transition in that corner region. So now that we have this unstructured domain, so now it's just a matter of doing translation extrusion again to create this prism block. So I'll let Travis go ahead and do that. So just before we finish off with this wake block, I'm just going to make Travis is going to do one more operation where he's going to grab this wake block and he's actually going to rotate it about the axis of the blade. So you can see he's going to change it to, he rotated about 10 degrees. So he rotated it, that would be clockwise 10 degrees. And so why did he choose 10 degrees? So, I mean, the way we determined 10 degrees is just to look at the actual tip speed ratio. So tip speed ratio, for those of you who don't know, is the ratio of the velocity of the tip versus the incoming flow. So in this case, if we were to do the analysis, we would be using a tip speed ratio of 5. And so just using some basic trigonometry, the resulting function would be the inverse tangent of 1 over the tip speed ratio. And so doing that, we come up with a value of 10. Now, I mean, it's not exact, but at least it kind of better positions our wake block where we anticipate the actual wake to be. So we can better position that. And because we have a lot of flexibility with the position of the block, that's the benefit of doing the hybrid technique, is that we can create these higher quality meshes where we want them and not be constrained by the outer topology, which he's going to show next, and how we can allow this to float. So we've done the high quality meshes in the boundary layer. We've done the high quality mesh in the wake, and so now Travis is going to create the framework of connectors and domains that he's going to use to create this unstructured block that's going to wrap around all this. And so this is going to take him another minute or two, just some again fairly basic operations in Pointwise. So I want to take this opportunity and maybe answer some of the questions that have been queued up. So one question from Gridar, excuse me if I mispronounce your name. He said, can we use the hyperbolic tangent variation while extruding it in the normal direction? Yes, absolutely. By default, the facility for doing extrusions is using just a geometric progression where you specify a delta S or and the growth rate. But the way to do non-geometric type distributions is what you can do is you can create a connector with whatever distribution function you want, and then you can use that connector to drive the spacing and the growth rate and the actual extrusion itself. And there's an option in the actual normal extrusion panel that you can toggle between geometric progression versus using a connector to drive the extrusion itself. Another question from Dorit Sobata. What is the maximum aspect ratio that is recommended for domains interfacing with structured and unstructured volume meshes? That's actually a really good question, Dorit. And when we get to the point where we catch up to Travis again, I'm going to kind of highlight some of that, what goes on. So this interfacing between structured and unstructured, Pointwise will automatically insert pyramids, and so you have to be a little bit careful with what's going on at the interface. So if you have, at least in my experience, if you have these high aspect ratio quads, and then Pointwise is going to automatically place a pyramid on top of that. If that aspect ratio is too high, if you can't visualize it, just sketch it out on a piece of paper, to draw kind of a regular pyramid on top of a high aspect ratio quad. And if that aspect ratio gets too high, you end up with some you get some triangular faces that have a very high included angle, and high included angles are a good indicator that you're going to end up with some poor quality tests. And so, I mean, again, it depends on the capabilities of your flow solver, but at least for me, just a very general suggestion. I try to keep my quads that I'm going to be interfacing to a TET mesh with, I try to keep them about 10 or below, and so an aspect ratio of about 10 or below. That's just kind of, from my experiences of creating some high quality meshes at that transition region. All right, so Travis finished creating that framework of connectors and domains, and so this is really the key to this whole hybrid meshing technique in Pointwise, is to the ability to create an unstructured volume mesh, but it can interface, like the question I was just answering, it can interface with structured domains on the boundary. So what Travis is going to do is he's going to create this unstructured volume mesh, what we call a block, and he's going to include not only these unstructured far field domains, but he's also going to include the outer part of that extrusion on both the hub and the blade, and that blade is where those structured domains are going to occur. And then, as he goes through and does this, he's going to also add the actual prism block itself. And because the prism block is kind of free-floating in space, is that, again, this is another terminology of ours, is to add a second face, and the second face is kind of, you can imagine, it's like subtracting the volume of that prism block, because those cells already occur there. There's no reason to recreate them, so we're just kind of, this is how we envelop that prism block in the unstructured volume mesh. So now he's created the block. So what he wants to do is we're going to go in the block solver, and the reason I want to go in the block solver is I'm going to show you what Pointwise does when it interfaces unstructured blocks with these structured domains that have these quad cells. And so he's going to go in at this junction between this collar volume mesh at the root of the blade and the prism extrusion. So you can see Pointwise will, in this block solver, Pointwise will render the outline of the pyramids. You can see them kind of in that light gray color. And by default, Pointwise will use an aspect ratio of a 0.5, so that just kind of dictates the height of the pyramid. And in this case, that the apex of the pyramid at this junction is actually piercing through the outer part of the prism extrusion on the hub, and that's a bad thing because if we try to initialize the volume mesh, Pointwise is going to complain that there's some intersecting surfaces. So this is just something to be aware of when you're doing these kind of meshes. So Travis is going to change the aspect ratio to a lower value so that you can see he brought down the apex of the pyramids, and so we don't get an intersection. So this is something just have to be aware of manually right now with Pointwise, but in the next major version that we're releasing a little bit later this year, this pyramid cross-checking will be automatically done, and you won't have to worry about having to manually back off the heights of those pyramids. All right, so Travis now is going to just the last few steps for creating the mesh in the near field. So he's just going to take the unstructured domains in the front and the back and create prism blocks, again, just for simplicity and also for reducing the cell count, upstream and downstream of this. Again, this is maybe a good opportunity for me to maybe to answer some of the questions that are starting to queue up. Lots of good questions. Thanks a lot, everybody, for all your questions. So I've got a question. How does Pointwise specify boundary condition at the structured and unstructured interface? Again, this is from Swati. In that case, Swati, I mean, because the structured and unstructured volume mesh is going to be point matched, that interface is actually kind of an internal domain, and so by default, that's part of the internal volume mesh. And so when you export this to your CFD solver, you export that volume mesh. There's no need to actually specify a boundary condition there because it's just going to be contained as part of the volume mesh. So again, I'm going to catch up with Travis here a little bit just to kind of cap off what he's done here. And so the last step in this case is to create the outer far field that's going to wrap around the near field. And again, this is just some fairly basic Pointwise operations. He's going to use a fully unstructured, again, because this is far field. And so the reason he's creating this separate far field region is that, ultimately we want to do maybe possibly two types of simulations with this. We want to do a moving reference frame simulation where we solve the near field in a rotating relative frame, and then we do the outer region in a fixed frame, or we may want to go all the way and actually do a transient simulation where we include the entire geometry. And in that case, that would be simply just a matter of copy and rotating the volume meshes twice to get the full wheel. So I got a question from Robert Moody. What options do I have if the geometry comes in as, say, 1,000 surface pieces of questionable connectivity, size, aspect ratio? Maybe there's some slivers and types. Do I need to clean up problems, or is there a quick way to determine if it is good enough without modifications? It's actually a really good question, Robert. It's actually we actually have our last webinar was dedicated to that question almost entirely, is how to clean up geometry in Pointwise. And just in general, I'll say that there's two ways you can do that. Yes, you can go ahead and clean it up and make everything watertight, but that's not a requirement to meshing in Pointwise. The alternative is to leave the geometry as is, create a mesh on top of that, dirty or sloppy geometry, and then we have tools for actually cleaning up the geometry itself. And neither of those methods are mutually exclusive. You can actually use a little bit of one or a little bit of the other. But I would definitely refer you to our last webinar, that's 2 webinars ago, where we were concerned with some of those topics on a naval application. All right, so Travis just finished up. He's all done. So before we kind of finish off here, I'd like to show you what the internals of that volume mesh look like, just to give you a feel for what things look like inside. So Travis is going to he's going to open up the volume mesh and in the examine mode. So he's going to look at some sort of examine metric, and he's just going to take a slice down the axis of the whole mesh, just to give you a feel for what's going on, where we have these coarse, large TET cells in the far field, and then in the near field region where he did those prism extrusion upstream and downstream, you can see those prism cells. And then if he ultimately gets to, now he zoomed way in, and now you can see the resulting extrusions from on the hub. as well as that collar region and the blade, and then how it transitions, nice and smoothly away. So we have these smaller tets that transition nicely with the hex cells and stuff like that on there. So at this point, Travis is done with the volume mesh. I mean, other than just setting boundary conditions and volume conditions, this is essentially ready to go into the actual safety solver. So, I got a couple more things to say before we get into the full-blown Q&A period. So, again, I just like to thank you everybody attending and your attention. So we had a question about will files be available? Yes, tomorrow we're going to put the grid files. We'll put our Pointwise file up there as well as the original geometry file. Maybe we'll put it the mesh in maybe some generic format so you can immediately try the mesh in your flow solver of choice, as well as the webinar that you're seeing today is recorded. I know Travis is going through relatively quickly, but you may be able to play and pause it and maybe kind of get an idea of what he was doing. If you have any more questions that you can't get out of the webinar recording itself, absolutely email or call us. You can email Travis and I at sales@pointwise.com. Those go directly to us, or call us at the main Pointwise number. We'd be happy to work with you one-on-one and on your and talk at length about your application. And just one last note: the Pointwise user group meeting 2011 is this November 8th to 9th in sunny, hot Fort Worth, Texas. Big thing for us is the rollout of Pointwise version 17. For those of you who aren't aware, version 17 is a pretty major release for us. It will be the first version of Pointwise that is absolutely feature complete with GridGen, so there'll be nothing you would need to go back to our older software with GridGen to use. Hands-on training, there'll be a day of training with version 17. We interact with some CFD experts from around the world, and if you submit an abstract and present, we waive the attendance fee for that. And so please go to pointwise.com/UGM to register and attend. So at this point, I think we're ready to maybe answer. There was a lot of questions I didn't get to. I apologize for that. So we'll open up the floor now to some more discussion. I'm going to let Rick moderate the Q&A session.
Yeah, we've got quite a few questions that people have typed in that are queued up that Chris will go ahead and answer. But if you have more questions that you want to type in, go ahead and keep doing that. Also, if you have a microphone and you want to ask a question verbally, just raise your hand and I'll recognize you. Right now you're all muted, but I can unmute you and give you a chance to ask your question verbally if you want. So we'll keep on going for a while here, answering questions both ways.
Okay, I'm just going to go through this fairly quick. I got one here from Andy Luke. Can you zoom in on the downwind hub blade junction? So I'm going to let maybe I'll get Travis to go back to the Pointwise cut and just zoom in, and we'll just maybe leave the display up there for everybody just to take a look at that. We had a question. What is the maximum capacity for the unstructured solver in terms of number of nodes produced? This is from Dorit Sabata. Really, that's strictly a function of how much hardware you can probably afford to buy. Pointwise is 32 and 64-bit on the 3 platforms we support: Windows, Linux, and Mac. And I've personally done, I've created a mesh recently. We were just doing some large grid testing. On a single workstation, our software is single-threaded, so it's not parallelized. I've actually done a 1 billion cell mesh, and so, and number of node counts, that's probably on the order of about 200 million nodes. So, and I did that on a single desk-side workstation that had, in that case, it had 90 gigabytes of memory. So, I mean, pretty much the sky's the limit. You can probably make meshes in our software bigger than you can probably afford to buy hardware on.
Okay, Chris, we've got one hand raised from Robert Moody, so I'm going to go ahead and unmute him and let him ask his question. Robert, did you have a question? Hello, Robert, are you there? Okay, I'm having trouble hearing him, so we'll just move on. I think you've got some more typewritten questions queued up there.
Yeah, I have a lot here. I got one from Darren Grove. I said, why did you choose to put a block behind the blade instead of adding a wake sheet and extruding off that? That's actually, I mean, there's definitely many ways you can do wake resolution. The reason I choose to put a block there is is again, is give me very precise control of the character of the cells, and because I'm inserting this in an unstructured block, I have complete freedom to place the location of the block wherever I want to. Now you could say, yes, I can do that with a wake sheet as well. However, the only way to insert a wake sheet into Pointwise right now would be using a fully unstructured, where you would just maybe create this unstructured domain and have a really tight, resolution on that, and then we can insert that in Pointwise. But actually extruding off a wake sheet is something that's not possible in the current version of Pointwise. But I mentioned V17 coming out later this year. That's a capability that will be coming to version 17.
Okay, Chris, we've got another verbal question from Darren Grove, so I'm going to unmute Darren. And Darren, you had a question?
Yes, I did. I actually typed in the same question twice because I wasn't sure you got my first one. That perfectly explains it, Chris. So
okay,
thank you. Kind of makes sense.
Yeah, absolutely. I mean, again, just to kind of clarify that the purpose of hybrid meshing is because we can make these kind of hybrid, blocks. That's an unstructured one where I insert whatever type of mesh I want. That it definitely gives me a lot more freedom as to where I can place certain cell types and cell zones, and so that we can, a lot more quickly, achieve it. And again, even in the case of a wake sheet, I mean, yes, that's, again, I'd say that capability is coming to Pointwise a little bit later this year. But if possible, I still feel that it's probably maybe a more accurate way to, if you can, to insert these optimally like a structured block. Give perfectly hex cells, because you can create the highest quality mesh you want with that hex, and then place it exactly where you want within that unstructured zone. And I think that's going to be one, like I mentioned earlier, is a more efficient distribution and number of cells, as well as a much better quality cell.
Okay, Chris, we have another verbal question from Haris Hamid, so I'm going to unmute Haris. And you had a question, Haris?
Well, my question is same about the cell skewness. You can see that the edges are cells are very skewed. So how to control the cell skewness?
You're talking about at the junction of that prism extrusion and the downstream side of the actual blade root?
Yes, yes.
Yeah, man, you have very sharp eyes, very astute. They're actually, yeah, right, and it's due to that. We tried to kind of mitigate it somewhat by adjusting the heights of those pyramid, but ultimately it's just the way that extrusion is coming off the hub, and it's kind of piling up against the back side of that. If that was, and I think in this case, Travis is actually displaying the color of the cells by maximum included angle. Now, I think if you were to turn on the histogram, I think you would show there's just barely a handful of these poor quality cells. I think there's like 5 or 6 in that junction. Now, if that was actually causing a lot of problems, now granted this mesh has about 6 million cells, so that's like 6 out of 6 million. Now, if that was causing you problems in terms of convergence, or you just didn't like it in terms of accuracy, I think my suggested way of getting rid of that would be to maybe go ahead and actually do a structured mesh on the hub, and then either do it and then manually create a structured block off that hub and have it made up with that collar region, and then you would have precise control of all the cells, and everything would be aligned all nicely in that junction. So that would be my suggestion, anyways. And I feel this hub isn't very complicated, so maybe to do a structured polynet would maybe take you another, again, if you were relatively proficient with our software, maybe another 15 or 20 minutes.
Okay, Chris, we've got one more verbal question. It's from Alberto Pellegrino. So, Alberto, you had a question? Hello, Alberto?
That's okay. If he doesn't speak up, I see his question in the queue, and he says, I didn't understand why you rotate the inner mesh of 10 degrees. And there's somebody else that asked the same question. So the reason why we chose 10 degrees, we rotated about the blade axis by 10 degrees, is because so the blade is rotating around in one direction, and we have the flow direction is going to be perpendicular, and so there's a non-dimensional value that engineers that are in this field use. It's called the tip speed ratio, and that's the value of the velocity of the tip when it's rotating divided by this axial incoming flow. That's called the tip speed ratio. So again, using just some trigonometry, looking at the triangle, the velocity vector triangle that those create, we can kind of roughly guesstimate where the wake is going to come off the trailing edge of that blade. So you can imagine if there's no incoming flow, blade is rotating around, the wake is going to be purely in the, looks like it's the X direction. So in that case, we would just make the block in purely in the X direction. But as that incoming flow magnitude increases, we know the wake more and more is going to get pushed in the actual direction. So what we're trying to do is just trying to guesstimate where we think that where the wake is going to be. And so in that case, using the tip speed ratio, again, using some trigonometry, I think I worked it out to be the inverse tangent of 1 over the tip speed ratio will give you that value of 10 degrees.
All right, Chris, there's one more verbal question from Mohammed Arifin. Mohammed, you had a question?
Yes, hello?
Yes?
Go ahead.
I have just one question, is that if the interface is somehow one-to-one ratio space, so is there any other way to solve the problem at the interface? I mean, what do you do if there is a hanging node?
So the question is about whether there's hanging nodes or if we don't have a point-matched interface between the blocks themselves. Is that what the question was?
Exactly.
That's really strictly a function of your flow solver, whether it can handle that. I mean, in my case, everything Travis showed today was point-matched because the majority of solvers, you know, maybe don't have a capability for doing that. So we were trying to be a little bit more general, but that's really just a product of what your flow solver is capable of doing. And lots of flow solvers have this thing that's called, I've heard it termed, general grid interface. So if you had that capability, it's absolutely possible to have a non-point matched blocking. And if that's a capability and you're comfortable with the accuracy that delivers, that may be even a more flexible way to do these kind of meshes. And there's, again, so just to clarify, there's no restriction in Pointwise that forces you to have all your blocks to be point matched. It's your choice. And to even go further, you may have saw on that last slide that I had, that figure from Tim Baker's paper, was the overset method and Pointwise, and it can be absolutely used for overset, where your solver has the ability to overset assembly, and so you can do that in Pointwise as well.
All right, Chris, another, well, no, it went away. Okay, there's no verbal questions right now.
Okay, so I got a couple more. I got one. Please display the azimuth wake region behind the trailing edge of the blade and the wake block. That's from Ed Vaughn, so I'll just let Travis do that while I answer some other questions. Got a question from Kelly Londenberg. Will parallel mesh generation be available in a future release? If so, how far in the future? Well, that's a pretty tough one to answer. I mean, all I can say about it is we've definitely, we're definitely talking about it. We haven't, we don't have anything on the books or anything planned, so I can't comment on an actual future date. But I definitely, maybe it's good, this is maybe a good way, good thing for me to actually comment on maybe a bit of the performance of Pointwise. So for structured meshes, Pointwise is extremely fast and very memory efficient. I mean, you can do, absolutely huge meshes on the smallest, workstation. Now, unstructured meshes tend to be a little bit more, memory intensive and compute intensive, but in general, it's pretty fast. So I mentioned before, well, here, I'll give you, maybe give you a better example. So one of the customers I work with on a relatively regular basis, we do fully viscous unstructured meshes on the order of about 150 to 250 million cells. So that's, I don't know, maybe 60 or 70 million points. And I can do those on a desktop workstation in an hour to an hour and a half. And so that's again, that's fully unstructured. So it's fairly fast. If you, this mesh here, these unstructured meshes, which contain 5 million cells, you can populate the blocks with those TET cells, and again, it depends on your workstation, but maybe a rough figure is 5 minutes. If you got something fast, it'll be literally just a couple of minutes. So doing unstructured is still very fast. Any more verbal questions, Rick?
There's no verbal questions right now. No. I'll just point out, somebody wrote a comment that the URL that we put for the user group meeting was incorrect. Instead of all caps for the UGM, it should be a lowercase UGM. So I do encourage you to go look at our user group meeting website, but make sure you go to the lowercase UGM.
Okay. Couple more here I'm going to answer. Somebody's asking about the ratio between the internal domain volume and the outer domain. I don't know what it is exactly. Like tomorrow, like I said, tomorrow all the grid files will be up online, so you're more than welcome to go check that out. Kind of along the same lines, could the mesh generator be used for OpenFOAM? Absolutely. I mean, it's just a mixed element mesh. Everything's point matched. There's no reason why you shouldn't be able to try this in OpenFOAM.
Maybe, Chris, could you guys open up the CAE menu just so they can see the solvers that we support?
Okay, I'll get Travis to go ahead and open up the CAE panel just to show you the list of solvers we support. I have a question from, again, excuse me, I can't pronounce your name, but I'll just ask the question. So can I use the T-Rex technology in this case? So for those who don't know, our T-Rex technology, that's actually just a shorthand name for anisotropic tetrahedral extrusion. Basically what it is a fully unstructured viscous boundary layer meshing technique. Now that capability in 3D is not available in Pointwise right now. It's in our older product, GridGen. Our license is allowed to use either or. So getting back to the question, can we use this technology in this case? Yes. I mean, we actually have some literature on our website. If you actually go to the T-Rex page on our website, and there's actually some images of a mesh I've actually did on this exact geometry using the T-Rex technology. So I got a question from Daniel Hung. Will version 17 be able to produce full prism layer with automatic anisolayer solver? T-Rex, I believe. Yes. So again, this just kind of goes along with the last question. Version 17, our version coming out later this year, again, feature complete with GridGen, will have the T-Rex technology, so you could technically do this fully unstructured with automatic boundary layer extrusion off the whatever surfaces you want, and then even has the option to recombine those TETs back into prisms in the boundary layer region if you want. So another question from Ed Vaughn, why is there a gap between the trailing edge and the wake block? Again, we just did that for ease of meshing. Now it's entirely possible to actually, we could have created that wake region completely attached to the backside of that actual boundary layer extrusion off the blade. We could have maybe extracted some topology off the trailing edge side of the outer part of that extrusion, and then we could have made it point match with the wake block itself. Now again, that requires a little bit more manual intervention, but it's absolutely possible. We just did it. This is a little bit more flexible this way because maybe if we were looking at the different tip speed ratios, we may be able to automate the repositioning of that wake block or something like that. And again, just for demonstration purposes, that was the quickest way for us to do it. But yeah, I mean, I think that would be maybe even a better way to do it, because then you would totally eliminate the TET cells in that gap region between the trailing edge of the boundary layer block and the wake block itself. Let me go through the questions here. Is any more verbal questions, Rick?
Nope, no verbal questions right now.
Hello, Rick.
There's another question that's kind of related to the just answered, and that is somebody wants to know if you can zoom in between the blade tip and the wake, and isn't the wake too far away from the blade?
So Travis, I'm going to get Travis to zoom a little bit closer to that wake region just so we can kind of maybe talk about that a little bit more. I mean, that's a good question. I mean, really that boils down to what you're trying to achieve in terms of accuracy. Again, we created a very simplistic shaped, first of all, we created a very simplistic shaped wake block. So if if you think it's too far away, or you don't like the fact that there's TET cells there, I think like the question I just answered from Ed about can you attach it, I think that might be the better approach in terms of again still using a hybrid technique, but we want to kind of eliminate all the TETs in that important wake region, because that's again where there's a velocity deficit, and we again this is all about reducing the pressure drag in that wake region. So that's definitely possible, and you could even go one step further, like I mentioned early on, as opposed to actually doing, creating this unstructured circular sector region and creating a prism block. Maybe again, just literally probably I would say 15 to 20 minutes is to create a structured domain instead, and then create this block in the wake that's point matched to the backside of the actual boundary layer extrusion. we got a question, just a general question about what maximum cell skewness do you recommend for high quality simulations? Oh, that's a very loaded question. It really, I mean, in general, it really depends on the, the sensitivity of your CFD solver. Some of them tend to be very robust with poor quality cells. And again, skewness is actually defined very differently in different types of flow solvers. For example, I know that, and there's also different types of skewness. There's so, I know from experience with Fluent, its measure, one of its measures of skewness is it has to do how far is the shape of the cells from being isotropic. So I think Fluent recommends something like a value of try not to have any or very few cells over a skewness of 0.9. Now OpenFOAM, its measure of skewness is a lot different. Being a cell-centered code, it's concerned with interpolating values from the cell centers and the faces, and so skewness is a completely different metric, and it might be a little hard for me to explain here, but if somebody's interested in that, I was actually at the OpenFOAM workshop about a month ago, and I gave a talk on a very similar talk I did today, but I gave a talk explaining mesh quality in OpenFOAM, and so you can go to the OpenFOAM workshop website and maybe download that presentation I give there that talks about that. So I got another good question that I probably kind of glossed over here a little bit. I'm new to Pointwise, so this is from Michael Barton. I'm new to Pointwise. When I create blocks, they are created as empty. How do I fill this block with text? That's a really good question. It's a bit of a different concept, maybe there's some other measures. So creating a block is essentially taking these domains that comprise a watertight volume mesh, and a block is essentially that watertight representation of those domains. Then as a second step for this is, and actually I should clarify that this is only necessary for unstructured blocks, is to populate that block with TET cells is a second step where you actually have to, what we call it, initialize the block. And the reason we do that is because it's definitely possible that maybe your TET mesh has a lot of cells, and so you can create this block empty, and then as a second step when you're ready to populate it, because maybe if you have 100 million TETs, it may take an hour, so maybe you want to do it at a later time. Also, it's another, I find it a very compact way to save, to cut down on the actual size of the file when you're saving it, and say, well, I'm not going to be using this mesh for a while. Let me empty the block so it has no cells, but the block is still there, and I save the file, and then and I can archive that file later, and then when later I retrieve it, I just have to click that button to repopulate the block. So that's just a concept that's specific to our software.
I think we're coming up on just about an hour, Chris. Do you have any more questions there that you need to answer?
Okay, so I got one more. Maybe I should go back to. I'll go back to that one slide. It's from Henry Vu. He says, "Can you again explain the accuracy advantage of using hex grids versus TETs?" You had a slide on this earlier, so I'm just going to let Travis go back to that discussion, and I'll have this as our last question. I think this is an important one. So, grid alignment. So what I have here is, you can see the curves, the colored curve I had is just representing the boundary layer profile. So this is flow over a flat plate. So we know that flow over a flat plate has no flow gradients in the axial direction, so in the x direction. So that means partial u partial x is essentially 0. It's really the flow gradient is in the y direction, so in the normal direction. So we have partial u partial y. That's where the gradients are contained. And so what I'm doing here is the equations themselves are, I have U cell plus a bunch of derivative terms, and so because I'm extrapolating from the cell center to the face center. That's the Taylor series expansion. It's a second order accurate Taylor series expansion to the face. And so in that case, because and the gradient again is totally in the vertical direction. But so that means that in our Taylor series expansion, there's no du dx, so those terms aren't present. So all I'm left is a partial u partial y delta y. But I don't have a delta y because because that face, again, it's being orthogonal to the flow gradient, that delta y is effectively 0, and that term cancels out. So I have almost a perfect extrapolation from the cell center to the face center. Again, just to clarify, I'm talking specifically about finite volume cell-centered codes where I'm trying to compute the value with the cell center, and to do so I have to do the integration So I'm looking. I need values at the faces so I can integrate around the boundaries of the cell. Now when I move over to the same exact setup, now I'm looking at a triangle. Because I have to go from the cell center and I have to go diagonally up to the center of that face, there's still a bit of a delta y because it's a little bit offset, and so those truncation terms are retained. Now, granted, everybody's like, well, I still want second order. Well, in this case, this is even higher order because those truncation error terms cancel. So that's generally why structured meshes, and particularly flow-aligned structured meshes. I think the key is both. You can't just say structured meshes and assume it's going to be better. The key is trying to get things flow aligned. And in general, we know that in the boundary layer, the flow is generally, for the most part, is attached. And so if we can do some sort of extrusion like I showed you and get those hex cells in there, you can get, at least a better quality resolution of the boundary layer by using flow aligned type mesh topologies. So again, I want to thank everybody. There's lots of excellent questions. I apologize for those I couldn't get to. There was probably at least 30 or 40 other questions I couldn't get to. So please email or call us directly, and we're happy to work with you one-on-one to show you what we did here today. Or if you want to go, if you're not current customers, we're willing to talk to you about setting up an evaluation where you can evaluate Pointwise for free, fully supported. Thanks for your time.